Good evening, my friends and followers. My name is Edward Wasrom, the tutor in Edwards Academy. This evening, I will bring to you an interesting development in macroeconometrics. I will bring to you a concept called Toda Yamamoto 1995. Recall in my previous video on how and when to take decision on the appropriate econometric approach while actually doing a study in time series research. I informed you that when you are exposed to conditions where you have combinations of series of different order of integrations, order 1, order 0, and order 2, that the appropriate method you are expected to use is the Toda Yamamoto 1995 approach. Toda Yamamoto 1995 causality text is a modified non-granular causality text and based on augmented K plus Z max, which generate an asymptotic vast statistics in the form of a chi-square distribution. Recall that the normal granular causality test is based on F statistics, and F statistics follows normal distribution. But when granular causality is faced with structural break, it breaks down, which is the reason behind the adoption of non-granular causality known as the Toda Yamamoto test. The Toda Yamamoto test is more robust test that takes care of issues relating to structural break in time series research. And the unique nature of the TY procedure is that it does not require pre-estimation for co-integration properties of the system and therefore avoids the potential biases being associated with the unit root test and co-integration test, since it could be applied irrespective of whether the series is integrated of order 0, order 1, or order 2. Whether the series is co-integrated or not, the Toda Yamamoto test is actually an interesting place to be. Like I said previously, the formula for the Toda Yamamoto test is K plus Z max. K in this context represent the lag length, while the D max represent the order of integration. So I'll move on to my eView portal where we actually give you an example or show you how to estimate the Toda Yamamoto non-granular causality test. Basically, there is no known icon, there is no known portal, there is no known procedure to estimate the Toda Yamamoto test in eViews, but there is a way we can actually compute or estimate Toda Yamamoto test using the VAR framework. To do that, this evening I'm adopting a study approach where I will be looking at the impact of population dynamics on economic growth in Nigeria. To proceed population dynamics in this study, I will be using fertility rate, mortality rate, and net migration rate, while economic growth will be proceed with the PCI, which is per capita income. In Toda Yamamoto test, the first thing you are expected to do is to perform the K. The D max, to perform the D max, which is the order of integration. And into that text, we actually used to perform the ADF text and also perform a confirmatory test with the KPSX to actually ascertain the highest order of integration. To do that in this research, I will actually double click on the mortality rate. I'll go to view, I'll go to unit root text. If I hit the OK button at level, I have actually tested the mortality rate is stationary at level. I will move on to actually perform the unit root test for the fertility rate. Fertility rate, we'll go to view, we move on to unit root text. Fertility rate is stationary at after first differencing. I think fertility rate is stationary. Okay, after second differencing, fertility rate is stationary after second differencing, given what we have here. Okay, fertility rate is stationary after second differencing because after second differencing, the T statistics is greater than the critical value at 5%. We'll move on to the next variable, which is the net migration rate. The net migration rate at level using the ADF is not stationary at first difference. We'll move on again. Is not stationary at second difference. We'll move on again. At second difference, the net migration rate became stationary after second differencing. So let's move on to the PCI. The PCI series is a value. Go to quick, you go to group series statistics, move on to unit root text, the log of PCI. Because it's a value, we decide to log it. We'll come over here, we'll click the level, we click OK. We have PCI, not stationary at level. We'll move on again to first differencing. We'll click on here, we'll click on tick level to tick first difference. We have a near stationary condition. We'll move on to second order. We'll move on to second differences. We click OK. We observe that our PCI became stationary after first differencing. So in all, we have a combination of order 2, order 0 precisely. So let me actually go to KPSX to ensure that order 2 is the highest order of integration, because it must actually perform a confirmatory unit root text with the KPSS and the ADF before you can conclude on the highest order of integration. To perform the KPSS, we start from the maternal mortality rate again. You go to view, you go to unit root text, you move on, you change this test type from ADF to KPSS. You leave it at level, you click OK, you hit OK, you look at it, the value here, the T statistics is higher than the critical value. You move on to first difference, move on to first difference, move on to first difference. The same thing is happening here. Then you move on to second difference, move on to second difference, move on to second difference. The same thing. We are now having a series that looks like this. Then we go to the net migration series. For net migration series, we go to unit rate, leave it at KPSS at level. We have 93% is higher than 46% stationary at level. We move on, we go to the fertility rate, we move on to fertility rate, we move on to fertility rate at level, we leave it at KPSX, we have it this way. We move on again, we go to first difference, we have it this way. We now move on to second difference, we actually have it this way. Then we'll move on to the log of the PCI, the log of the dependent variable. We'll go to quick, go to series statistics, you go to unit to test the log of PCI, log of PCI. We hit OK. We go to level, we hit the OK button. We have 1.2 greater than 0.4. We move on to this way. Go to unit to test first difference. We hit 22% less than 26%. We go to second difference. We move on to second difference. We still realize we have issues like this. So basically, the highest order of integration for this particular estimation we want to do is 2. So we have noted that our D max is 2. So to actually identify our K, which is our order, our lag length, we go to quick, we go to estimate var. In this var estimation box, we specify our model log of PCI, MMR, NMR, and we have FER, fertility rate. Then the next thing to be done is to hit the OK button without changing anything. You hit the OK button. Once you hit the OK button, you'll be exposed to vector auto regression estimate. You go to view. From view, you go to lag structure. From lag structure, you move on to lag length criteria. You hit the OK. Lag specification, lag to include, leave it at 3 in default. You hit the OK button. You'll be exposed to a result that looks like this. This is what they call the lag length result. The lag length result looks like this. This is the lag length result. This is your lag length result, and this lag length result, our attention should go to the last three results. The last three results are AIC, so SC, and the HQ. So wherever you find the asterisk, that is the lag length. If you trace this asterisk horizontally leftward, you will now get to 5. So given this particular result, we have here, since these asterisks are actually within this area, if you trace them horizontally leftward, they will now interact with the 5. We now say that 5 is the lag length, that the lag length according to the 3 information criterion is lag length 5. So we are going to have k equal to 5, while d mass equal to 2. So 5 plus 2, we are going to have 7. So our Toda Yamamoto estimation, we are going to estimate with lag length 7. So to move on, we move on to quick again, or you can move on to quick. You can also move on to estimate from this result. From this result, move on to estimate in the exogenous box. In this exogenous box where you have the C, you will now have to incorporate the appropriate calculation of the Toda Yamamoto. We have lag 7. So since lag 7 is our new order or formula to be used, we code it like this. We have the dependent variable -7. All other variables, you have lag length, lag 7. You code them with lag 7. We have fertility rates, code with lag 7. So without changing any other thing, we have the dependent variable PCI -7, the independent variables, all the independent variables -7. Without changing any other thing, the lag length here, we have lag length 5. Change the lag length from 2 to 5 without changing any other thing. If you hit the OK button, you'll be exposed to a result that looks like this. From this result, you move on to view. From view, you go to lag structure. From lag structure, you go to Granger causality block exogeneity text. If you hit the OK button, you'll be exposed to an output that looks like this. So this is your Toda Yamamoto result. It appears like a normal Granger causality results, but the blockchain exogeneity word test. This is the outcome. I'll copy it neatly to my Microsoft Word, where we actually offer a very clean interpretation to it. This is my Toda Yamamoto output. This is my Toda Yamamoto result. I am presenting it today. My Toda Yamamoto output. So the next thing to be done is to interpret this output in line with the appropriate standard. And to have that done, we actually need to observe the normal procedures for interpreting Granger causality with modification. Recall that this estimation was done this day, the 25th day. We are doing it because we actually want to be sure that readers and students are able to learn the little tricks involved in it and to interpret this result. If you look at this result appears in cluster of each of the variables. Invariably, each of the variables are endogenous in nature. If you look at it, this is the equation of the PCI. This is the equation of the maternal mortality rate. Then this is the equation of net migration, and we also have the equation of fertility rates. So in these different equations, these variables are all independent variables in different equations. So to interpret this particular results, you look at the first equation of PCI. In the PCI model, none of the variables under consideration is significant at 5%, but at 10% net migration rate affects PCI. But in economics, you should be consistent in the level of percentage you are referring to. Recall that in economics, we assume that there's always 95% accuracy, so we make provision for 5% error, which means that we are making reference to 5% significant value. At this point, we have 10%. If I should interpret on 10%, we cannot say that there is an impact between net migration and PCI, that net migration actually stimulates the PCI at the tune of 10.53854, and when net migration increases, PCI increases. If the a priori expectation of this result is that PCI will have net migration will have a positive impact on PCI, then this result will be interpreted in line with the a priori expectation. But if the a priori expectation is that net migration will have a negative impact on PCI, then this result we should also be interpreted in line with that particular a priori expectation. Then if you actually look at the second result, we have the second equation where MMR is a dependent variable. We have the first one, PCI has an impact on MMR because the probability value of PCI is significant and the chi-square of 19.74 is actually higher. That means that as PCI increases, the MMR net maternal mortality also increases, and this also may also be in line with the a priori expectation. But I believe that the a priori is that as countries try to increase their productivity, there is a tendency of them having their maternal mortality reduced, so it's expected to have a negative impact on maternal mortality. So if you go to the third equation, none of them is significant to actually cause a reduction in net migration, whereas in the fertility equation we have the two of the variables in the fertility equation to be statistically significant. PCI is significant determinant of fertility rate, and maternal mortality rate is also significant causation or on maternity on fertility rate. That implies that as PCI increases, fertility rate increased by 11.929872. As maternal mortality increases, fertility rate also increased by 15.28402. So this is actually how we interpret the non-Granger causality output. The Toda Yamamoto test, we just avoid the use of the word bidirectional and unidirectional causality, and most of the words we use in Granger causality. There is no other way to estimate the Toda Yamamoto in EView. When we go to Stata, I will actually teach you how to do it with Stata, but at the moment this is how you estimate and code the Toda Yamamoto in EView. Thank you for listening to our video. Thank you for subscribing to Edward's Academy. I promise in my subsequent videos I will bring to you fascinating development in macroeconometrics. Thank you and God bless you for listening.